Hello and welcome to Conversations in AFM. I'm Dr. Elizabeth Kugler, a science communicator and your host of today's conversation, Applications of BioAFM in the Life Sciences. To talk with us about BioAFM and applications of AFM is our guest, Dr. Körnig, application scientist at the JPK BioAFM Center at the Bruker GmbH. He's a biophysicist who did his PhD at the Max Planck Institute of Colloids and Interfaces in Potsdam, in Germany. And since about 2014, he is an application scientist at JPK Bruker. His focus is on biophysical applications of atomic force microscopy, or AFM, as we will be referring to it later on, such as imaging of single cells and biomolecules, dynamical studies using high-speed AFM, and nanomechanical analysis using force indentation and microrheology. So first, a huge thanks, Andre, for being here with us today. And maybe you could introduce yourself a little bit to our listeners and tell us who you are and what excites you about AFM technologies.
Yeah, thanks, Elizabeth, for introducing me, and thanks for having me here and getting this new exciting experience of doing a podcast. You introduced myself already quite well. So I'm an application scientist at the BioAFM business unit, as we call it in Bruker. And AFM technology, I got hooked by it in my master's thesis, or at this time it was still diploma thesis. So I studied physics and realized that the dry matter and material stuff is maybe a bit boring. So I got attracted by more the life science. So having kind of an impact to something living was quite interesting. And then so I went to a biophysical institute in Bielefeld, actually. And there, my first technique was AFM. Then I did a lot of other stuff, but basically the first technique you learn, you kind of get hooked, or I got hooked with. And after the PhD, I found that this nice opportunity to start as an application scientist at JPK at this time. And I seem to like it because it's now 10 years that I'm doing this and progressing in different fields. This is what keeps me excited with this technique.
That's amazing. I think it's great to hear that you've been working for 10 years with this technology and it still excites you, which means there's obviously lots of different aspects to study and to do and to learn about, which is always great. And so today we've got this unique opportunity to ask you loads of questions. So thank you again for being with us here today. And I think the main thing that always fascinates me about atomic force microscopy is that it is really a beautiful kind of marriage between physics and biology. Like you said, you studied physics originally, but you're now more like in the BioAFM and application side of things. So it's really bringing together physics and applications of the technique. And obviously, for those listeners who don't really know too much about BioAFM, I think it's also important to point out that BioAFM is very special because it obviously allows you to perform AFM on samples without the need for a lot of sample processing, but it allows you to study really very small molecules like DNA and viruses to living cells and tissues. So you can have this huge range of samples that you're actually studying. And you very briefly touched on your journey into AFM and that you really kind of, still fascinated about it. But what do you think makes this technique so special, and why, what do you think is so important that we still need to develop it, and what are you really working on?
There are now two things. As an application scientist, I often go to also conferences and kind of present it and show the advantages of this. But what I kind of like it's that it's I don't want to do this. I want to make it maybe even more general. So what I like on it is that it's quite easy to understand what's going on. So compared to fluorescence or SEM or like some other advanced techniques. So basically, I always say, or one analogy I use is just like the finger of a blindfolded man. So you can touch things and you can see the topography or kind of how things look like, and you also kind of can feel how stiff things are. So basically, you can touch things and you see, okay, this is softer and this is stiffer. And this makes it or I like it also for then going into the biological application. So where people study more their cells or their tissues or their samples, and then they don't want to think about what's the technique doing. So, and with the AFM, I think it's quite easy to explain how it works, so that you touch things and you get out how it looks like and how soft and stiff it is. And I mean, as you just said, the other interesting things is that you can go to really small things. So I mean, for biological materia, single atoms are not so interesting. This is more for the material AFM people. But as you say, you can do single DNA strands, viruses, but also the big stuff. So you have a large range of applications in this biological world. You can basically measure anything, any biological matter. I mean, there was even one crazy scientist that wanted to put a whole arm below an AFM. So I think it didn't work out completely because the arm is just moving too much for the sensitivity of the AFM. But in general, you can put anything below it and start measuring. I mean, this is what you also said, that it's kind of easy to start using it, because you just have this little cantilever that touches things. So the little finger just in a very small size. And this is, I think, what makes it so interesting to kind of use it in the biological world.
That sounds absolutely amazing, especially the arm measurement. I think, we're all crazy scientists, but I'd never heard about someone putting a whole arm under an AFM.
So we had to do some adaptation to make it a bit larger, kind of the whole stage and so on. But this was kind of an idea. I don't know why he wanted to do it. I just saw in kind of also the picture, and that this was his idea to do it. I think it was about some skin measurements or something like this. Yep.
I love the idea, but it probably would have been easier to take like a skin biopsy rather than put the whole
arm
under the microscope.
But then it's in vivo,
True. Very good.
Want to measure in vivo, yeah.
Absolutely, which also is probably one of the big things, right? That you can in BioAFM literally measure in vivo in the normal healthy context, right?
Exactly, yeah. So this is exactly. So the other advantage of this now more for science-related things, I mean, biological matter, often you need to have some medium around, so you have to be in liquid, which makes all the electron microscopy a bit more difficult. And this in the AFM, whether you immerse this cantilever in some liquid or medium or whatever, is rather easy. So, and also heating and temperature is no problem. So this also makes it, very very well suitable for biological applications. So I think it was a good idea to bring this AFM technique that was traditionally more on the material side, to bring it in the biological world, because it's it makes a lot of things quite easy to adapt, and this advantage having it in close to living conditions or native conditions is a huge advantage, and makes it easy for biologists to use it.
Yeah, which is great. So it's like a lot of like plus points, obviously, for BioAFM. But maybe can you talk also a little bit about like what challenges are there, like in comparison, for example, to material sciences? Like you said, material sciences, we mainly look at like small molecules, and BioAFM is more like large structures, which might have more movement and are in vivo. But what other challenges are there that we could think about?
Challenges is that it's living, so it might change over time, or it will change over time often. I mean, depending a bit on whether you section it or whether you fix it or so on. But in general, as I said, you always want to measure things, how they change, and if things are changing, well, you need to also cope with this. So sometimes this makes a bit of an issue. And then, I mean, the analogy with the finger I was saying is you need to be able to touch it. So it has to be somewhere on the ground, let's say, or on something, and you have to be able to touch it from above, let's say. Yeah. So this is kind of the two things that make your life sometimes hard. So if you want to image something with optical microscopy, it can be in the liquid swimming around, and you would see it. With AFM, it kind of needs to be on the substrate and should not swim faster than you are scanning, for example.
But in comparison to EM, it's probably very little kind of sample construction. Yes, absolutely.
As I said, so this is exactly in EM. Often you need to dry, you have vacuum, and so on. There is also the environmental one, but in general, exactly. So sample prep is quite easy. I mean, but just thinking about it, sometimes we do have problems where people say, can you measure this? And then, but is it somehow on the surface? And then, this is the only thing where we run sometimes into communication issues of what's the sample preparation about. But mainly it's the point that it has to be somehow lying down to be able to touch it.
Yeah, which is also a nice point to bring up. Like sample preparation is obviously one of the most important things in microscopy to get that right. Maybe you can mention a little bit about like your experience, obviously really wide and huge. Like you probably had loads of things under your AFM. Maybe you can talk a little bit about the sample preparation, like what's the challenges and like what's some very common applications and kind of common mistakes you see in sample preparation.
Yeah, the common things are probably mechanical analysis. Mistakes in sample preparation is a bit what I said. So I just had recently somebody that wanted to measure some bacteria. That's why I was saying with the swimming around that they kind of didn't fix well to the surface, so they would just start swimming off while we were touching them. Actually, this was also an issue during my PhD, where I started with some magnetotactic bacteria, trying to measure them, and it was kind of impossible to get them there for sufficient time to measure them. And this is actually also what I like here in this field, that it's kind of a good combination of a lot of disciplines that you have. The physicists that kind of like the technique, the chemists that help you with surface modification, and the biologists that have their samples. So it's quite a interdisciplinary field, I would say.
And you have obviously also been working for a long time, so you have seen like the trends about 10 years ago and like the later ones as well. So have you maybe seen like some change in the type of samples that people are looking at, or like what are kind of more new applications that people are using AFM or BioAFM for?
There's a huge development. One is basically speed, so image, kind of how quick you can take an image. So when I started AFM, one image would take 10 minutes or something like this. And now there's a lot of fast imaging AFM on small molecules. So there the sizes matter. So the smaller, of course, the faster you can go. So basically you have to slow down the recording to be able to see it, because our eye just sees with like 20 to 30 frames per second. So basically you can record faster than you would be able to see. So this is a development that was when I started with AFM, kind of not possible or not imaginable that you can speed it up so much. Which then again, what we talked about, I mean, would not maybe on the bacteria, but then things can move around quicker and you still can see what they are doing. So this is then also quite nice to open up kind of a field of dynamics. The other trend is, I mean, this always has been. Well, not always, because in the traditional AFM, it was just topography when it started. But then people realized, okay, as I said, you have the finger and you can sense whether things are stiffer or softer. So a big topic over the last 5, 6, or maybe even like it started maybe already 10 years ago, but kind of it got more and more evolved, is mechanical analysis. So basically that you can differentiate between soft and stiff. So this goes into cancer research, where cancer cells have a different stiffness than the non-cancer cells. In whole tissue sections where you can do mechanosensing. So kind of this opened up a huge field that it's quite easy to use these techniques for this mechanical information that, as I mentioned before, doesn't really have any comparison in other techniques, let's say. The last one is basically the huge development in how easy it is to use the system. I mean, I guess this happens in a lot of techniques, but kind of when I started, it was the geeky physicist that did his whole PhD with the system. And now it's more and more that, just anybody can get a measurement out of it. I think this is a bit the development that fluorescence microscopy took already maybe 10, 20 years ago, where before you needed to adjust your wavelength and you need to know what's going on. And now basically people just press on a button and want to have their GFP. And this is a bit where AFM also goes to, that people are more interested in the sample itself, and they don't really want to know what's the whole technique behind it. So they want to know their Young's modulus or their mechanical properties, but they don't really want to know how it's going on. So this fraction becomes more and more. And of course, for this now being part of a company that provides these tools, this is a big topic to make it more robust and more easy to use, and therefore more reliable to use.
Yeah, I think there's lots of really interesting points, especially as you mentioned, it's becoming more easy to use and probably also more commercial systems available for people to use. Whereas like 10 years ago, probably a lot of people had to self-build microscopes, especially high-end and specialized microscopes.
Exactly.
So it's great to see it really come to the market. Obviously
Yeah.
not easy, but it is now. You can buy
Well,
it.
to use it in the end. I mean, yeah,
Yeah.
exactly. So the usage of people, so you don't have to have so deep knowledge about the system itself. It still would give you the results that you are actually interested in.
Yeah, which is ultimately the most important thing, right? So you also spoke about mechanosensation, and I think I'm really into biophysics and obviously mechanical systems. So I was reading a lot in preparation for the podcast, and I think for me the most interesting study was mentioned in one of the recent ebooks by Bruker, JPK, and it was talking about multiparametric imaging of fibroblasts. And fibroblasts are one of my favorite cells. So I would love if you can tell us a little bit about, what's the study looking at in fibroblasts with AFM, and what is multiparametric imaging in the context of that?
Well, yeah. So fibroblasts exactly. It's quite handy cells. They are quite robust. So that's why we also use them for general imaging. Because you can try a lot of things with this. So I kind of like them as well. Because if you're not a biologist, you might treat things a bit differently. So and they forgive also the let's say physical approach of using them. So we have some colleagues that are biologists, and they sometimes shake their heads when I just use it as a tool, let's say, to get it out. But so this is about the fibroblasts, and this kind of the ebook or the chapter, of course, focuses a bit more on what's the AFM then doing with it. And this multiparametric imaging is basically what I kind of mentioned before already. So we have now the access to not only see the topography of the cell. So how does it look like? Is it rather large? Is it spread? Does it have a lot of fibrous network in it? Because actually often you kind of can also poke into it because you apply a force. So you would even see the fibrous network within the cell. So you have there also a bit of information. And also these other parameters are then the stiffness or adhesion, or you kind of can get a lot of other information out of it. But most people would use the so-called Young's modulus. So you apply a so-called Hertz model on it. So you do when you move your cantilever down on your cell. So you kind of come from the top, you go down on your cell and poke into it, let's say, and out of this, how your force increases while you indent, you can then apply a certain model. And now I'm talking again like a physicist to then get the so-called Young's modulus out of it. And this is kind of the information of how stiff it is. Yeah, basically. And what you also can do, so this would be one, so you don't get just topography, you get also stiffness out of it. What now people do is, so because this Hertz model is quite simple, it has a lot of assumptions that, actually don't apply so much to the biological world. But now we also, and I think this is also highlighted in this ebook, is a so-called microrheology tool. So we do now not only poke it, but basically move the cantilever a bit up and down, and see how your sample reacts on it. And if it's kind of only elastic, it would react differently than if it's viscous. So basically, then you have a small drag. So this is a parameter you cannot get out of it. Or what other people do, I think this is also a bit highlighted there, is that you can kind of now connect some molecules on your cantilever, and while you're imaging, you would see counterparts of it. So you kind of can also measure ligand and receptor interaction while you're imaging, and you can put it locally where you see it. So this is what this multiparametric imaging is telling. So you don't get only the topography as it is known from the AFM, but you can access a lot of information basically by taking just one image and analyzing the force curves, as we call it, that you have just while you're doing the imaging.
That's amazing. I love when people just talk science and go right into it. That
Yeah,
was great.
sorry. Yeah, I
Thank you so
get a
much.
bit geeky. Yeah, but yeah, I mean, as I said, I'm doing it since 10 years, and I still kind of like it. So yeah, there's a bit of passion in it.
And that's the best thing that could happen, isn't it?
Yeah,
Yes,
yeah.
absolutely. I also had the question, what is your favorite cell type?
Well, yeah. So this fibroblasts, I kind of I like them, as I said, because they forgive me the maybe not sometimes well by like the treatment. Yeah, more delicate cells would maybe not forgive, but fibroblasts often forgive you my maybe not so well handling. Um, and yeah, we kind of have them a lot here. So maybe that's also the, I kind of yeah start liking, or you like things the more often you have to do with it, and the more kind of nice results they give you. And so I think fibroblasts is, yeah, from the cell type, I would say yeah, the
Very
ones I
good.
use most, and that's why probably my favorite cells.
That's great. Team fibroblasts. Very good.
Yeah,
Very good.
exactly. Team fibroblasts.
Yes,
Yeah. Yeah.
awesome. So now I want to move on with you a little bit more to speaking about BioAFM and Bruker Nano to talk a little bit about more the technologies that you use specifically and that are developed in-house. And one very big application is obviously, one consideration is that AFM is used in industry, materials, and life sciences. And one very special thing at Bruker Nano is obviously the tapping mode. Could you maybe explain what that is to our listeners?
Yeah. So there's a tapping mode and there's peak force tapping mode. I mean, I go a bit on both of them. So tapping mode, yeah, is kind of doing an oscillation in resonance, and this we use a lot for this fast imaging. What I mentioned before. So images get quicker. This in all the industries is getting important. So I mean, in life science, as I said, you want to have molecule interactions, seeing on a very high level of speed. And basically, of course, in materials, I mean, I yeah, silicon wafer people, um, they also, I mean, the quicker you can measure, the quicker you get your results as well. And then there is also this peak for stepping mode, which basically Bruker got very, very big on and developed it. And this is kind of, yeah, a similar mode that what I was explaining before. So you have access to you can generate force curves out of your image, and this gives also this access to this multiparametric imaging. So this also gives you a lot of results like indentation and forces and deformation and so on, which also in material science, I mean, maybe not on the wafers, but kind of in, let's say, polymer sciences and so on, is very, very important. And I mean, I saw once like kind of a graph how much publications were using now this peak for stepping mode, and it's increasing quite a lot because it's also quite good to use and gives you a lot of information.
And there is another very important mode that is also special to Bruker, which is the quantitative imaging mode.
Yeah, so this comes a bit by the fact. So basically, I mean, I started actually for this JPK. I mean, we are this JPK BioAFM business unit, as we call it. So JPK was before an own company, and there this quantitative imaging mode was developed. And so basically, and now we joined Bruker, and this is now kind of the Bruker mode for this, as it says, quantitative analysis. It has the advantage that the cantilever always comes from the top, which makes it easy for samples that are not so well fixed. So, for example, in the beginning I mentioned the example of the bacteria, these magnetotactic bacteria that I couldn't image at all. I maybe with this QI mode, it would be now more possible because it's less. It's kind of more gentle to your sample, and it doesn't push things so much around. And as well, it's also giving these quantitative information out of your sample. And what we realize, I mean, this is a bit what we also said. Okay, we want to make it more simple and so on. It's a quite easy to use mode because it doesn't have so many parameters to adjust. So it's basically you just have two, 3 parameters that are also quite intuitive. So you have a set point, meaning how much force you apply while you go down. You have a z-length, how you go up. So it's kind of even what I said before for people that don't know so much. I mean, sometimes you want to even change parameters, and those parameters you easily understand compared to some other, sometimes AFM parameters where you have feedbacks and so on, which are kind of a bit more complicated to understand what's going on. With this one, it's quite quite easy to use. So it's easy and powerful. What else do you want?
Absolutely. The easiest thing or like the most powerful thing for scientists
Exactly.
is good. Yes.
Exactly.
And for those who are still intrigued about that mode, do you think it is most well suited for soft or sticky or highly structured samples? Or when would the QI mode be really important, and when does it make the most sense? Like what kind of samples are we talking about?
So for me, it's, as I said, even for me as a kind of experienced one, it's the go-to mode if I don't know what's my sample about, because it just, as I said, it doesn't move things around. That's why the words that you said. So if it's very soft or highly structured, so or you might push things around, so loosely attached things, there it's quite powerful. And also sticky samples, you then just increase the C length, so meaning how much you want to go up. Is quite easy to understand why you do it, and that's why if you don't know the sample, and I mean the only drawback I could say, it's a bit slower, but it's a very stable mode. So and kind of, I would say, I mean, I'm coming from the JPK world, and I'm using this mode a long time. Kind of, it's the easiest, as I said before, the easiest and very powerful mode. So you get a lot of information out of it. You don't have to set it up so much, and it's for any sample prep that you don't know whether it works well. If you can't measure it with the QI mode, probably other modes will be very difficult, because there you often push things more around, or the interaction is too strong or too soft and so on. So I'm using it for, let's say, every sample that I can find.
Interesting. So it's really more like a exploration mode, but also a high-end data analysis mode.
In the end, it's what you want to do with it, So kind of exactly, you just can start it, and then it depends on how deep you want to analyze it. And the only thing is, that I said, I mean, you don't get the 50 frames per second. This is then another mode. But as it's quite stable, I mean, this I also remember when I started with AFM, when you had all these feedbacks, it was like you sometimes, the image took 10 minutes, and you were hoping in the last 2 minutes that you don't run out of feedback and the image quality doesn't decrease over time and so on. And this year it's basically very, very easy to use and very stable. So you can, and this we also realize, so it often doesn't matter so much how long the image takes. If you just can come back after an hour or two, or then you have 10 images, then you're fine with it. So
yeah, that's great. And I mean, we've spoken now about quite a lot of different things, and I know it's always very hard to predict the future. But I would love to hear what you think is maybe like in the next 5 years, where is AFM developing into? Is there like something very special about BioAFM? Where do you see really the future of the technique?
I don't know whether 5 years, but the development goes a bit. I mean, so all this ease of use and making it easier, more robust, and more reliable. So I think one field where it starts pushing it. So right now it's a very scientific instrument. So basically, research institutes, universities, and so on and so forth. But I think if it's, it's used a lot in medicine research, for, as I said, cancer research and so on. So basically, I think there will be the lab where, or the development, if it's getting more robust and more kind of easy to use, it will emerge into also medical research. There it is already, but maybe even into medical centers. So this might be one thing that it will go to, and this includes that things have to be more, let's say, easier to use, because then somebody working in the hospital then literally doesn't want to care about how the results come out of it. It just wants the result. So this, I think, is a big field where things might change in the near future. How near this future is, we're gonna see, but I think this will be a big development.
So it's all about the bench to bedside translation, which is great. Thank you so much for all these really, really interesting insights.
Thank you.
So that's all that we have time for in today's conversation, but join us next time where we will chat with Professor Kristina Kushevierok on maybe my second favourite cell type, which are endothelial cells. See you then.
This podcast was sponsored by Bruker BioAFM, part of Bruker Nanosurface and Metrology Division. Bruker is a manufacturer of scientific instruments for life sciences and materials research, as well as for industrial and applied analysis. If you'd like to learn more, please visit www.bruker.com/bioafm. This podcast was produced by Keep It Science.